Hello everyone. Today we will talk about another method of solving the static force problems, conservation of power. In some cases, we only want to know external forces acting on the system rather than internal forces on the system. For example, action and reaction forces on the joints are internal forces. This method is quick and straightforward compared to free body diagrams. In the last lesson, we have used the method of free body diagrams to analyze the equilibrium of a machine by isolating its components to drawing a free body diagram of each component, and then applying equilibrium equations to figure out all the forces acting on the machine. In this class, we will learn about another method of expressing the conditions of equilibrium based on the conservation of power. This method is derived from the principle of virtual work, and the virtual work is based on the concept of the work done by force of moment. After explaining of conservation of power, you will get an idea. This method is more direct and easy than free body diagrams. So I want to take a brief talk about the principle of virtual work and the work done by forces before we go learning the method of conservation of power. When a force acts on an object over a distance, it is said to have done work on an object. Physically, the work done on an object will cause a change in kinetic energy. We can see the figure. dr is a small displacement. Its magnitude is ds, and theta is the angle between the force vector and the direction of moment. In mechanics, a force F does work on an object only when the object undergoes a displacement in the direction of the force. The work du done by a force F over a small displacement dr is a scalar quantity divided by F times ds and the time cosine of theta. We can also represent the work as the inner product of the force F and the displacement dr. The unit of the work is Newton meter, or called as joule in the metric system, and in the empirical system, it will be foot-pound force. It is interesting to know that the forces we encounter every day are mostly variable in nature, which it is defined as a variable force. In the case of a variable force, when an object undergoes a finite displacement along its path from R1 to R2, the work of the force is determined by integration. The amount of work is equal to this integral expression, where parameter s is the arc length of the curve. In practice, we can say total work is the area under this graph bounded by position S1 to S2. We often meet some systems the work is done by a constant force Fc in a straight line. It means that the force Fc have a constant magnitude and acts at a constant angle theta from its straight line path. Then the component of the Fc in the direction of displacement is always Fc times cosine of theta. Therefore, the work is proportional to displacement as like this. Consider the rigid body which is subject to a couple moment. A couple moment is defined by the force F times the moment on R. We shall know that the general motion of a rigid body is a combination of translation and rotation. Let's take a look at a translational motion of a body first. We know that the couple consists of two equal and opposite forces whose lines of action do not coincide. When a body translates, the work of each force is produced by F times ds. Because two forces are equal and opposite, the positive work of one force cancels the negative work of the other. Total work will be 0. Let's go see the rotational motion of a rigid body. When an object rotates by the angle d theta around point O, the work done by each force is the force F times its displacement ds. Since half of r times theta is the distance moved by point on the ring, total work is done this u equals to the force times the distance r and times d theta. We know a couple moment n is equal to the force times the distance r. So work done by the couple du is equal to n times d theta. If the couple moment is not constant, the work is determined by integration. When the body rotates in the plane through a finite angle theta from theta 1 to theta 2, total work is integral of the moment n from theta 1 to theta 2. If the moment n is constant, the work will be proportional to the angular displacement. The work done by forces and moments are measured in the course of dynamics. Unfortunately, I hear Professor Chen say you do not learn dynamics yet. Since they go beyond this close contact, I strongly suggest you remember the equations shown in these slides. If you want to know more details, please read dynamics textbooks. If you have any question about dynamics, don't fail to contact us for answers. Let us talk about the concept of virtual work. What is virtual work? It is defined as the inner product of the force and the displacement delta U. Virtual work is imaginary work, so you are not doing real work. You are just doing an imaginary thing here. Is imaginary work done when the object subject to a number of forces is moving a small imaginary distance? Several forces acting an object like here. In this case, we have a mass sitting on a horizontal surface. Force 1 push to the left. Force F2 push to the right at the angle theta to the horizontal line. Gravity pulling it down with ng. And the normal force N push back. So there are 4 forces acting on this object. Let's now assume that we are going to move the object an imaginary distance. We will call it delta U. The question is, how much virtual work is done? In this case, we have 4 forces, so we are going to have 4 components added to the virtual work. The first force F1 is pushed to the left. We have the magnitude of the force times the magnitude of the displacement and times the cosine of the angle between them. Here, the angle is 180 degrees. Then, we have the second force F2, pushing to the right at the angle theta. Again, we take the magnitude of the force times the magnitude of the displacement and times the cosine of theta. The other two forces, the force of gravity Ng and the normal force N, both forces are perpendicular to the path, so no work will be done. When the object is in equilibrium, total work done by all the forces is equal to 0. So if F2 is given, we can apply this equation to figure out the unknown force F1 like this. This slide shows you an example to determine reaction force R acting on point PB when given force P is applied at point PA. Total virtual work done on the entire rigid body is 0, since the body is in equilibrium. In this case, the force of gravity of the body is negligible. Three forces are acting on the body: external force P and the reaction force R and the reaction force FO. We know no work is done by reaction force FO because point O cannot move. External P pushed to the right. The object will spin by an angle delta theta around point O, and the forces are pushed back to provide the motion. The work done by external force P is equal to force P times the virtual displacement of point PA. When the angular displacement delta theta is small, the distance of point PA moving is the distance A times delta theta. Because the displacement is opposite to the direction of force P applied, negative work is performed. Work done by reactive force R is force R times the displacement of point PB, which is the distance B times delta theta. If the object is in equilibrium, total work done by force P and R is 0. Therefore, we can get reaction force R is equal to P times A and divided by B. This example is to determine the force Q exerted by the vice on the block when given force P is applied at point C. We assume that there is no friction in the system. Consider the work done by the external forces for a virtual rotation delta theta, where delta theta is a positive increment to theta. Internal forces are acting on the revolute joints C and B. Because the work done by internal forces cancel each other, the work is equal to 0. Reaction forces at the revolute joint A have displacement equal to 0, so no work will be done. And the reaction forces act on the slide. We have force N perpendicular to the side axis, and the couple N along the lead axis to provide the slide rotate. Therefore, both force and moment perform no work. So, in this case, only the forces P and Q produce non-zero work. The displacement of point B, XB increases, while the displacement of point C, YC decreases. Thus, total work is the sum of minus P times delta YC and minus Q times delta SB. If the mechanism is in equilibrium, total work delta U is equal to 0. Force Q can be determined by these equations. In practice, virtual work only considers the work done by external forces. It means that internal forces acting on the mechanism are not involved. From the geometry, we can express SB and YC in terms of theta, and differentiate with respect to theta to get the small displacement delta XB and delta YC. By using the method of virtual work, unknown force Q can be figured out like this. In the previous lesson, we know that the method of free body diagrams need to break the system into components for determining equilibrium equations, but it is not necessary to dismember the system in the virtual work method. The relationship between external forces can be determined directly without concerning internal forces and reactive forces. So this method is easy, and it is particularly useful for determining an unknown external force in the equilibrium system. When we use virtual work, we need to know the relationship between small displacements of points that external force act. In this case, delta SB and delta YC, sometimes it is not easy to figure out their relationship. We know power is defined to be the rate at which work is performed. It is derivative of work over time. The work dW done by the force is equal to the inner product of the force F and the displacement dr. We know the displacement dr is divided by the time dt is the velocity. So power can also be regarded as the inner product of the force F and the velocity v. For rotation, power is the moment n times the angular velocity omega. Since we already figured out the velocities and the angular velocities in the mechanism through the velocity analysis, it is convenient to use power instead of work to compute the unknown external force acting on the mechanism. In a metric system, the unit of power is watt, Newton meter per second. When measuring in the imperial system, the unit is either foot-pound force per second of horsepower. Horsepower is defined as power that a horse gives when pulled. We need to know 1 horsepower is equal to 550 foot-pounds force per second. Conservation of power is quick and easy. Conservation of power is quick and easy method of computing the ratio of input force of torque to output force of torque. This is particularly useful if velocity analysis have already been performed. Conservation of power stands that the input power equals the output power. When a given mechanism is in a conservation of power, the following three assumptions must be satisfied. There is no energy losses in the mechanism. It means that there are no energy dissipation. In a mechanical system, energy is dissipated when two surfaces rub together. It means the work is done against the friction, which causes heating of the two surfaces. There are two energies stored in the mechanism as it moves. This means that there are no springs in the system, and because of the change in the centers of gravity of members, the energy associated with potential energy is negligible. The velocities are small enough, or the masses are small enough, that changes in kinetic energy can be neglected. In the mechanism, if only input force Fi and output force Fo are applied, and Vi and Vo are respective velocities of their points of application, we can get the equation of conservation of power is that the inner product of the force Fi and the velocity Vi is equal to the inner product of the force Fo and the velocity Vo. If only input torque Ti and output torque To are applied, where omega I and omega O are angular velocity of the input and output links, respectively, the equation of conservation of power will be like this. We can move the output loss from the right side to the left side of the equation, so those loss can be regarded as input loss. A mechanical system may have many input forces acting on it. We can add up all the powers. Total power will be equal to 0. Or we may have a mechanical system which many input forces and moments acting on it. Thus, we add up all the powers generated by forces and moments, and the total power is also equal to 0. Let us review some important issues about the conservation of power. If forces or moments cannot produce the work, they also cannot generate the powers, because the power in physicals is the amount of work done divided by the time. This figure shows no work done by reactive force and the internal forces, because the normal force Fb never does work. The forces Fo acts on the point without movement, and the resultant work done by the pair of internal force is 0. So this force also cannot generate the powers. Only external forces and the torques do the work in the mechanism, so they can generate the powers. Before we conduct the conservation of power to solve the unknown external force of torque, we need to use a velocity analysis. For example, analytical closure equations of the instant centers of velocity to compute the velocity of points which external force act on, and the angular velocity of links in which external moments act on them. We can see conservation of power only gives an equation, so it is easy to solve the problem. I will use 3 simple examples to briefly explain how to adapt the conservation of power to solve the problems. This example is a slider crank linked, subject to two import forces at point C and P respectively. First, we need to determine velocity of points C and P through velocity analysis, and then use the conservation of power to solve the unknown force. The equation can be expressed as the sum of the inner product of force F1 and the velocity Vc and the inner product of force F2 and the velocity Vp. In this case, if force F1 is given, we will solve force F2 by this equation. This case is a linkage is subject to four external forces F1, F2, F3, and F4. We assume they are all import force. First, the velocity of points P1 to P4 needed to be determined. When this linkage stays in equilibrium, the summation of the powers generated by these four forces will be equal to 0. Therefore, we can solve the unknown force by any three given forces. We have an elliptical trainer machine like this figure. When you stay on the machine, you put your feet on the foot pedals and put your hands on the handle grip. There is a 25 pounds flywheel in the back of the machine. Up to 24 resistance levels you can choose from the operator screen. It means you can either increase or decrease the moment to change the forces exerted by your feet. When you stride on the machine, there are 1, 2, 3, 4 forces and one moment acting on this machine. This is 5 powers produced by forces, and the moment can be summed, and the total power is equal to 0 in equilibrium. Since we can figure out the velocity of all points and the angular velocity of the mechanism, so we can quickly get the load that we're interested in through this equation. This is an example 14.7 of the textbook for analysis of the slider crank mechanism. In this case, the piston rod can be considered to act at point B on member 4, and the driving torque acts on the member 2. To obtain a quick estimate of the forces, we will neglect the effect of the weights of the components. This is reasonable because those weights are much smaller than the piston rod of P, 21,000 and 314 pound force. The equation of conservation of power is regarded as the sum of the inner product of torque T and the angular velocity omega 2 and the inner product of force P and the velocity of point B on the link 4 is 0. Let us assume that link 2 is rotating clockwise. The velocity of point B will move upward. Then P and V4 are parallel and in opposite directions. So, we obtain the formula T is P times BV4 divided by omega 2. Here, instant centers of velocity are convenient to compute the velocity of BV4. We use the Kennedy-Ehrhart theory to find the instant centers I12, I14, and I24. They are located as shown in the figure. We know the velocity of B4 is equal to the velocity of I24, and the velocity of I24 is the distance I24, I12 times omega 2. The distance I24, I12 can be scaled from the drawing of calculated as 7.713 inches. Substituting the values into the formula, we can get torque T as 164,600 inch-pound-force in clockwise direction. This is example 14.8 for analysis of the four-bar mechanism. Input torque T12 is applied to link 2, and it is resisted by torque T14 applied to link 4. The problem is to find a relationship for the mechanical advantage of the mechanism in terms of the mechanical geometry. The mechanical advantage is defined as the output torque T41 divided by the input torque T12. Its value always is positive. The power equation is the sum of the inner product of torque T12 and the angular velocity omega 2, and the inner product of the torque T14 and the angular velocity omega 4 is equal to 0. From this equation, if T12 and omega 2 are in the same direction, then T14 and omega 4 must be in the opposite directions. For the mechanism advantage, we only consider magnitude. Na is equal to omega 2 divided by omega 4. From the instant center of the velocity, we can locate the instant center of I12, I14, and I24. The instant center I24 comes to two bodies in plane motion, which have the same instantaneous velocity in each member. Thus, we can get Na as the distance r I24, I14 divided by the distance r I24, I12. The following slide will give the other three examples. This is a four-bar linkage. This case gives two input torques, 200 Nm acting on link 2 and 20 Nm acting on link 3. The weights of links are considered here. They are 20, 30, and 25 for link 2, 3, and 4 respectively. The input angular velocity omega 2 is 2 radians per second counterclockwise. All the positions of joints and the center of gravity of links are known and represented in coordinates. This problem is to find the output torque tau for 1. First, we need to check how many external loads are acting on this mechanism. From the force diagram, we have two input torques, tau12 and tau13, and the output torque tau41, and three weights, W2, W3, and W4 of members. Here, only output torque tau41 is unknown, so we can use the conservation of power to determine it. For this method, we need to know the angular velocity omega 2, omega 3, and omega 4, and the velocity of points P, 4, P, H, and Q, which the weights W2, W3, and W4 act on them. If omega 2 is given as 2 radians per second, we can use velocity analysis to get omega 3 equals minus radians per second and omega 4 equal 1 radians per second. And the velocity of point P, H, and Q like this. Then the output torque tau 41 can be solved using conservation of power. For conservation of power, we know the sum of powers generated by the forces and the torques equal to 0. We have tau 12 equals 200 Newton meter and tau 13 equals 20 Newton meter. All the weights are given and they point downward, so they have negative y components. For the planar mechanism, the power generated by torque is equal to the torque times the angular velocity, and the power generated by force is the inner product of the force and the velocity. So we get this equation to solve input torque tau 14. In this case, we need to find output torque tau 41. Torque tau 14 and the tau 41 have the same magnitude and the opposite directions. So we flip the direction of input torque tau 14 to get output tau 41. Tau 41 is equal to 375.5 Newton meter in a counterclockwise direction. In this slider crank mechanism, there are 300 Newton of input force F14 acting on the slider 4 to the left. Again, the weights of the links are considered. This figure shows you the position of the mechanism. We can use them to solve velocity through velocity analysis. The problem is to find the input torque tau 12 of link 2. In this case, we have input torque tau 12 and the input force F14 and the 3 weights W2, W3, and W4 of members. Here, input torque tau 12 is unknown. Using velocity analysis, when the velocity of point C is given as minus 4 meters per second, we get omega 2 and omega 3 equal to 7.5 and minus 2.5 radians per second, respectively. The slider 4 cannot rotate, so omega 4 is 0. Then the velocity of the points P, H, and C are figured out like this. Since all velocity and angular velocities are known, we can use the conservation of power to solve torque tau 12. We have a force F14 equal to 300 Newton, and the weights of the links like this. Substituting the load and the velocity into the equation of conservation of power, we can get input torque tau 12 equal to 125 Newton meter in a clockwise direction. This case is a double slider mechanism. Input torque 200 Newton meter is acting on link 2. Once again, the weights of links are considered. The input angular velocity omega 2 is 2 radians per second. This figure shows you the position of the mechanism for determining velocity of points. We need to find output force F41 acting on slider 4. In this case, we have input torque tau12 and output force F41 and the 3 weights W2, W3, and W4 of members. Here output force F41 is unknown. The angular velocity omega2 is given as 2 radians per second counterclockwise. Using velocity analysis, we can determine the angular velocities and the velocities of block along the slope and the link too. Here we know omega3 equal to omega2. Then the velocity of the points P, C, and B are figured out like this. All velocities and the angular velocity are known. Then we can use conservation of power to solve output force F41. We have input torque tau12 equal to 200 Nm and the weights of links like this. Substituting the loss and the velocity into the equation of conservation of power, we can get output force F41 equal to 3100 Newton to the left.